So good afternoon, everyone. Welcome to another Talks at Google event. So thank you all for joining us today. Today we're very pleased to host paleoanthropologist and National Geographic adventurer Lee Berger. Dr. Berger leads the paleoanthropology research group at the University of Witwatersrand down in South Africa. And among his many discoveries include the Australopithecus Sediba. Again, I guess clearly Latin was not my strong suit. It was more written in French. It would have been better. And also his work on the Taung bird of prey hypothesis. Dr. Berger he's taking a break from his research in South Africa to tour on his latest book, which is actually entitled The Skull in the Rock. It is a book intended for a wide audience that chronicles his discovery of the recent human ancestor skeletons and also his integration with Google Earth, of all things. He uses our tools to advance the field and also to advance our knowledge of human history. So please join me in welcoming Lee to Google.
Thank you. Thank you very much. Thank you. I just have to say that on behalf of pretty much the entirety of the scientific community, we probably owe more to your organization as an open access and open window into new areas of science than almost any other on the internet. That includes, the normal things you think of like Google Earth and Google Scholar that we depend on now almost completely as scientists, but also just Googling, which is a lot of fun. This sort of story that I'm going to tell you has a lot of those components in it. I'm going to tell you a story about a discovery in human origins. I'm a paleoanthropologist. I look for early human ancestors. I actually look for the rarest sought-after objects on the planet. I'm in a field of science that actually probably has more scientists in it than it does objects that we study. There are literally just a few thousand of these incredibly precious objects. Most of them are just fragments, tiny little bits and pieces. About 80% of the record of human origins in Africa represents isolated teeth. The remaining, say, 18% of that represents little bits and pieces of postcranial bones, of which we almost have had no complete elements from the neck down. Those skulls and stuff that you see on National Geographic and such, those are incredibly rare, number in just a few dozen. But this story is a story of some success in discovery, and while parts of it may seem like a eureka moment and a sort of what wondrous luck, like many great discoveries that happen, it begins in failure. I was, in the late 1990s, I was privileged enough to win the first National Geographic Prize for Research and Exploration. When I went to receive that medal in Washington, I was hauled up into those sort of magnificent offices up on the top floor of National Geographic, sat across from Gilbert Grosvenor, the then CEO, and Bill Allen, the powerful editor of the magazine. And they said something I hope all of you hear sometime in your life. They said to me, you can have anything you want, any amount of money you want to do anything you want. Now, they, of course, meant that within some reason, I presumed, but I knew exactly what I wanted to do. I wanted to apply technology to the search for these incredibly rare fossils and the sites that they come from. And the reason I wanted to do that so badly around 1997 was a series of technological events that occurred at that time that made it more accessible. One was the readily available handheld GPS. Now, things like the highly expensive Trimble GPS had on the box that it could get you to within the remarkable distance of something like 15 meters on planet Earth. And it cost thousands and thousands of dollars to do that. The other thing that happened at that time was that NASA had released its digital satellite images. And I could afford down to the 30-meter pixels that they had. And I think most of you would remember back in those times that those sheets cost in the neighborhood of $10,000 a piece for one sheet. And we had to get new computers at my university to even run them. I think they were something impossible, like 300 or 400 megabytes a file that we had to run at that time. But there I received this grant to go do this expedition utilizing this technology. And I set off across southern Africa, but also concentrated some of my work in an area right outside of Johannesburg, South Africa, that's now called the Cradle of Humankind, a UNESCO World Heritage Site. It wasn't then. It was a dolomitic limestone area that stretched for about 60 kilometers in length and about 10 in width. And from that area, which is arguably the most explored area on planet Earth for these early hominid fossils, continuously since 1935, had come some of the most fantastic fossils, but from a tiny number of sites. By that time, there had only been about 14 fossil-bearing sites for these early human fossils, but only about 4 of them were considered really of any serious value. So it was in that environment of looking for these things that I began to utilize this technology, not only do the first GPS coordinates of sites, because we didn't have them. They were all map coordinates prior to that, but also to find new sites. And over a 3-year period, I did find new sites in the area. I managed to find 4 new fossil sites in that area. I know that doesn't sound like a huge number, but remember the context of only knowing of 14 fossil sites, and remember that it was the most explored area on planet Earth for these very things. I found an additional 30 caves that were undocumented. We had about 30 non-fossil bearing caves documented in that area, and I thought this was pretty good. And so as we moved into the late 90s and early 21st century, I began digging some of these new sites with the hopes of them producing some of these extraordinarily rare fossils. Now, let me tell you just how important even single finds are. When I first went to Africa in 1991, I found 2 fossil hominid teeth, 2 single teeth, at a site called Gladysville, right in the middle of this area, and it made National Geographic magazine. Can you imagine? It was the first new site in 48 years, and that's the kind of rarity that people like me deal with in their day-to-day search. So as I began to explore these sites, I did find a few bits and pieces, which made me pretty happy, but I did not find anything extraordinary by the time we moved into the early 21st century. Now, having said that, I have to qualify that most of the people that do what I do will never find what we seek. Can you imagine going into a field of science where there's probably a 99.9% chance that you will never discover a single element of one of these early hominids in the wild? You literally can count the scientists who've actually physically discovered these in Africa on sort of 2 hands and have some fingers left over when you do that. So I did this digging, but I work at a university. And for anyone who's ever worked in the academic or university environment, universities live off things like nature and science papers, these high-impact papers. And finding little bits and scraps wasn't getting us into those. And as we reached about 2005, 2006, my university made the decision to begin moving away from my exploration unit that I had established to search for these sites and move into an area of science driven solely by technology to replace that. I was going to be effectively retrenched. They couldn't, of course. I was a tenured professor by that time. But they were moving in this new direction because a lot of critical things I don't have to explain to this audience were happening at that period. Processing power was becoming enormous and readily available. Computers, things like geometric morphometrics, the ability to handle these big data sets that were produced by CT scans, 3-dimensional exercises were coming into vogue. That's what was getting on the cover of Nature and Science, and that's where my university started moving. They started searching for a director, and eventually in 2007, they actually found someone to effectively replace me, a young man who had been my former student. I think some of you in technology will sympathize a little bit with that sort of transition that occurs very quickly, but it was an exciting period. We bought equipment, we bought tons of these new computers, very expensive software, and we even started bringing in a whole host of young people to start building a lab that no longer really focused its full energy on finding new fossils, but studying those that had been discovered over the past 70 or 80 years. It was going to be a retrospective thing as we moved into this new world. And there I found myself in December period of 2007, surfing the web looking for a new life. I was kind of looking for where I would find myself in the future with all of the kind of things I've explained, and it was at that moment that I became the last human being on Earth to discover Google Earth. Now, as most of you did, what did everyone do when they first discovered Google Earth a long time before I did? You look at your own house to see if you're lying naked by the swimming pool, right? I wasn't. Then you look at places that are familiar to you, and sometime in that journey, you find that amazing white box there on the left-hand side that has those GPS coordinates that you can stick in. And if you've got some, you stick them in and you fly out of outer space right to this singular fantastic point. Well, I had some of the most expensively obtained GPS coordinates on the planet. And I eagerly put the first ones in, and it zoomed in from outer space in that great zoom in and landed on nothing. The second one, nothing. The third one, nothing. I had useless GPS coordinates. It did not take me long to Google why they were useless. Of course, the United States government had owned those satellites in the late 1990s. They put deliberate error into them. And that, combined with the error in my relatively primitive handheld GPSs, created a form of a compounding error. And all of my data points were off by dozens, if not hundreds of meters. They were useless. I'd spent 3 years of my life and several $100,000 of National Geographic's money, and I was sad for a while. I was probably most sad about having to call up National Geographic and explain this. And so I spent January, February, and March moving the points from their incorrect position to their correct position because I could actually see the sites that I intended to do. Amazingly, the area where I'd concentrated my research had 5-meter resolution on Google at that time. And I could see the sites. I knew the area very well, and I could actually see the physical sites. And it was in the process of moving those dots from the wrong place to the right place that I began to discover something amazing. I first started thinking I saw patterns in the distribution of these various caves and various fossil sites. It seemed that the fossil sites seemed to cluster together in unusual ways. And I also learned, through correcting that error, what a cave site and then what a fossil site looked like from outer space. And I began to think that if that's a cave, this looks like a cave. But I knew it couldn't be. I had walked over that area over the last 17 years prior to that. Everybody, every big name in paleoanthropology has explored this area. I knew there was nothing to find. But by March of that year, it bothered me enough that I created a list of targets. And I did something very human. I went as far away within this region as I could get from the site of Gladysville, where I'd spent the last 17 years looking for these things, because I knew there was nothing there. I knew that area as well as my own backyard. And so I moved away from there, actually into a little town called Krugersdorp, actually the city limits, with this list of first targets. And on my first day out in March, I found 21 new sites. 21 sites that no scientist had ever seen before. By July of that year, I had found 600 new sites that no scientist had put a pin on, 40 new fossil sites. So we went from effectively, say, 17 or 18 fossil sites that we knew of to well over 70 of them in just a matter of moments. It was an incredible, incredible period for discovery. Everyone was very excited because suddenly we had these resources in front of us, this long potential that could last decades, hundreds of years. And I truly thought that that was going to be my contribution to this field, this discovery of this mass of resources, when by the end of July, I moved back into the area around Gladysville. And of course, immediately, I began finding sites. All in the area. I had missed them. They'd been right in front of my eyes. And on the 1st of August, I moved into the area that you're about to see as this camera zooms up, an area that I knew I wasn't going to find anything in, even by that age. Because down in this valley, back in the late 1990s, when I was doing that National Geographic expedition, I had found one of those 4 fossil sites. It was 1 kilometer away from Gladysville, 1.5 hills away from where I'd spent the last 17 years. And I had been on this road that runs in here literally hundreds of times over the last 17 years. However, I saw these targets, which you see being highlighted right now, and by that time, I suspected that that was what caves and potential fossil-bearing caves looked like. So I drove down this road with my dog Tao, and as I got to right here, I realized that I was going to make a discovery of at least some cave sites, because there was an old lime miners trackway that somehow all of us had missed, running right up to this particular little grove of trees. I heard you all gasp when you saw that, I know. But The reason I gasped when I saw that is it shouldn't have been there. Anytime you see a grove of trees like this, what you're actually seeing is a disturbed area of soil. It means that this dolomitic terrain, which is like 2.6 billion year old limestone, is very tough for trees to grow in. When you see clusters like this, particularly of two types of trees, white stinkwood and wild olives, there's a light one and the dark one there, you know that there's disturbed or collapsed systems underneath. I walked into that and I saw this shocking thing. No, you don't have to gasp all at once when you see that. What that was a tiny little hole in the middle of that grove of trees. That hole is about 2 by 2.5 meters. It was very unusual. It was a hole dug by the lime miners. They'd found it. They'd known there was a collapsed cave there. They'd put in 3 drill holes and 3 dynamite blasts. They'd blown up some rock in a typical way in their search for lime in these caves. But they'd done something then I had not seen before. They left it alone. And I'd almost never seen that. I turned the first rock over that I came to, and there was an antelope humerus, an arm bone, sticking in this concrete-like rock infill. I was stunned. I was less than a kilometer from where I'd spent the last 17 years. I was less than 200 meters from where I'd found a site in the 1997s. I had been there. And I could tell no other scientists had been there because we leave tells. You know, we pile little rocks together. We sort the things when we find them. But I was on a mapping expedition. So I looked around. I saw there were other fossils. And I took that terrible picture. I took an accurate GPS coordinate, some notes, and walked up the hill and found 46 new caves. 46 caves in this little hidden valley that no scientist had seen before in the center of the most explored area on planet Earth for those very objects. I was stunned. I went back to the lab, and we'd had a tragedy just a couple of weeks before this. The young man who was going to come and take over and my position and change this whole organization into this high-tech organization was killed in a motorcycle accident in London. And we were devastated because we were rudderless. We'd already hired people. We'd spent enormous amounts re-equipping to go in this direction. And a young man came into my office, a young Kenyan named Jobe Kibby. He said, would I take over his postdoctoral supervision? Charlie was going to be his postdoctoral supervisor. And I said, no, Jobe, I won't. You know, you're a lab guy. I'm a field guy. I can't teach you that. But I've just found this site. And if you want to learn to be a field guy, let's go out, let's take a look at this site and see what it has to offer. And so we went back out there. On the 15th of August, Jobe, myself, my then 9-year-old son Matthew, and my dog Tal went back to that site, walked up to it, and as we walked up, I told them how I discovered it, and much the way I've just told you. We got to the edge of this pit we were looking down into, and I said, okay, guys, go find fossils. If you find any fossils, give me a call. I'll come and identify them, and let's see what the site has. And with that, Matthew and Tal are gone. This is a huge game reserve. There's leopards and giraffe and zebra and antelopes and stuff, and I think he's off to chase some. I'll see him at lunchtime. So I turned to Jobe and I said, I bet the lime miners left this alone because they did the same thing I did. They found this site first. In the bottom of the hill, they start digging it. It's a 4-minute walks up the hill or something, sees all these other caves. He comes back, they blast, nothing really looks good. They take up, and they had destroyed every single one of those other caves, just destroyed them. And as I finished saying that, Matthew said, Dad, I found a fossil. Matthew was 15 meters off the site in high grass, and I almost didn't go and look. I almost didn't go and look because I knew absolutely what Matthew had found. Matthew had found an antelope fossil. Because for every one of these early human ancestors that we find, every one piece, we find 250,000 antelope fossils. But he's my 9-year-old son, and like you all want to encourage fossil hunting. So I wandered over to him. I got about 5 meters away, and I saw this, and I knew that his and my life were going to change forever. Because he was holding that little block. This was taken moments after that. In that high grass, you can see there was nothing else around it. It was seen at the base of a lightning-struck tree. But what I saw sticking out of the side of that rock from 5 meters away was this. Now I got you to gasp. No one gasped. I knew exactly what that was. That was an early human clavicle. That's this bone right here. It's your collarbone right here. And I knew instantly, they're really easy to identify. Firstly, only a few mammals have them in Africa. Bats have them because they fly, it was too big. Moles have them because they dig, it was too big. And primates have them. And only amongst primates do you ever see this very characteristic S shape, a sigmoid curvature. And at that particular moment in time, I happened to be the only world's expert on hominid clavicles. I'd done my PhD on them. I did my PhD on them because they were so rare that there were only bits and pieces of fragments left. I, in fact, did my PhD on the clavicle, the proximal humerus, and the scapula because no one else wanted to, because we didn't have any in the fossil record, and I was looking at one. Matthew says I cursed. I don't believe that. But I took the rock and did what any of you would do. You know, what else could this be? And I turned it over, and sticking out of the back of it was this. And that was completely unmistakable. That is the lower jaw in a canine, maybe the most identifiable tooth in a jaw of a hominid sticking out. I could see other bones, and then I was very excited. I might have actually cursed then, because I knew that I had the real possibility of holding in my hand what Matthew had found, a partial skeleton. And at that point, there had been approximately 7 found in all of history from anywhere in Africa. You would know some of their names. Lucy, the Turkana boy, Littlefoot, the Dakika child, Lucy's child, and then the remaining 2 are so fragmentary they only have numbers. That is, any piece of a head associated with any piece of a body of a single individual. We're very generous with the definition of partial skeletons, and I was probably holding one. I called the South African Heritage Resource Agency because there's actually cell phone coverage at the site to get permission to take it out. We got it back to the lab, this concrete-like rock. My preparators started preparing it. Within days, we realized Matthew had found a skeleton. And we knew a lot about it almost instantly. We could see that it had, this jaw in it, and it was a child, probably about 11 to 12, 13 years of age. Its third molar wasn't erupted. Its limbs had not finished growing. We could see the growth lines, the unfused epiphyses. It was hugely exciting. It was the upper part of a child. It was a magnificent moment. There was much rejoicing at the Institute. You can literally build institutes around a discovery like this in ours. So I had to wait until I heard that I was going to actually get the permit to work the site. On September 3rd, I got the call that I would get the permit. On September 4th, we all went back to that site. Everybody from my university that had a PhD or master's in paleoanthropology, biological anthropology, archaeology, or who liked dogs, went back to the site. Because as I told you, we don't find these things. We spend our lives not discovering them. And I think everybody there, 14 of us went, had the idea that, you know, if a 9-year-old can do it in a minute and a half, this is our moment. 3 hours after arriving there, we had found nothing that we could definitively call a hominid. In and out of that hole, you can see how tiny it was. We couldn't find anything that seemed to associate with this block. We couldn't put it back in place. We couldn't find anything that we could definitively say wasn't an antelope or something, and we were devastated. Now, in South Africa, I come from a sort of British culture, an English culture there. So when times are really bad in that culture, we break for tea. And so we did break for tea. We went, sat under the tree, and I walked back over to this pit. And I stood there staring down into that hole. And I was trying to reconstruct that moment. Maybe 100, 110 years ago, a blast must have just gone off. The rocks are scattered out here. And how could a rock get from in here to over there, back in the high grass where Matthew had found it? And I began to have that hideously ugly feeling that maybe this didn't come from here. What if that rock had just fallen off of an old ox wagon or something, coming from one of those other 46 caves that had been destroyed? And I was devastated. And as I was staring at that, visualizing that moment, the sun came up so it shined just along the back of that. And there, sticking out of the wall that we'd all been next to dozens of times, was a proximal humerus of an early human, sticking right out of the wall. Remember, I did my PhD on them. I know what they look like. I didn't say anything, though. I climbed down into the hole. I walked towards it. I got about 1.5 meters away from it. I realized that the scapula, the shoulder blade, was sitting in articulation. I still didn't say anything. I put my hand on the wall, and 2 hominid teeth were lying loose and fell out into my hand. Then I said something. And everyone rushed down in there. We were hugely excited. We suddenly realized that our paradigm had been wrong, because lying all around us were blocks like this with actually the proximal femur. We had been anticipating failure when in fact we were sitting on a treasure trove. Well, that has changed everything. From that extraordinary experience, I didn't realize that what I was looking at was not the skeleton that Matthew had found. It was a second skeleton, because never before in all of history had 2 skeletons been found in the same place. The one I found, we knew immediately after we took it back to the lab and began to prepare it out, was actually an adult skeleton. It had a fused epiphyses, so I could see that it was an older individual. It would turn out to later be a female, an adult female. We would later find Matthew's skeleton lying just 50 centimeters above that position. And so this little site in the past several years that I would eventually call Malapa, which means my home in the Sotho language, has produced extraordinary results. And also, we've been very fortunate because we've discovered it at a time where we've been able to apply extraordinary technology to it. This looks like a video to you. It's not a video. It's actually 21 million three-dimensional coordinates, each accurate to about 1.5 millimeters on planet Earth, that we can actually take and place every find back into context. If we'd found it 6 years ago, we could not have achieved that sort of technology application. In April of 2010, my team and I announced that these skeletons were actually a new species of early human. We did it in a special edition of Science, and of course my colleagues all forced me to show this image because, you know, for scientists, getting your fossil on the cover of Science is like for a rock star being on the cover of Rolling Stone. So they forced me to put this up here. But the preservation is extraordinary. At that time, we had these skeletons. We named a new species called Australopithecus sediba. Australopithecus is the genus name. We had to accept an already existing one that we felt it associated with. Sediba means source or wellspring or natural spring. And you'll hear why we named that in just a moment. As incomplete as those look at that time, they were both independently the most complete early hominids that had ever been discovered in the history of science, both more complete than the famous Lucy fossil. The site would yield preservation that we could not even imagine just a few years ago. I hope you can see the quality of the musculature, the preservation of that bone that we would then know was 1.977 to 1.98 million years old. So you're looking at a 2 million-year-old fossil. That is the most complete early hominid skull that has almost certainly ever been found. There is amazing preservation that goes beyond the bone there. We have found organic preservation there. Some of you might have seen we announced the discovery of calculus and tartar on the teeth just a few months ago in the journal Nature, and inside of that were food particulates. So never again will a scientist like me guess at what they ate. We know that they ate fruits and nuts and seeds like you would expect. They also ate bark, interestingly. That isn't that uncommon. That's the kind of thing that actually happens. But it's that level of preservation that's extraordinary. We may have even found skin. We may have even found early hominin skin. Watch this space early next year. Last year, we published more of this material in Science in another special edition, more of the extraordinary fossils, and these skeletons became then works in progress. The female on the left you can see is remarkably complete with critical bones that we had never before seen in the fossil record. He looks pretty incomplete, only at about 40%. My wife, who's a medical doctor, a radiologist in fact, is just finishing her PhD in paleoanthropology now, I guess because so she had something to talk about over the dinner table. But she did it on scanning the blocks and rocks, and in doing that, the very last block that she scanned a few months ago had the remainder of his skeleton in it. So we now know that he will be almost completely complete, something unprecedented at that time depth, really unprecedented out of the last few thousand years. They don't look anything like they should. Sediba is bizarre. It could be because they are so complete that we have been misreading the rest of the record. That is, we've been underestimating things like limb length and the shape of them. Or it may be that we have found truly one of the most mosaic transitional fossils and unexpected species that ever existed in that critical time period. Because at that moment, it's when we transition from these early Australopithecines like Lucy to our genus Homo. They have incredibly long arms. Here you can see the arm of a chimpanzee on the left-hand side. In the middle is Sediba. That is a pygmy, and they're all scaled to the same size. You can see how Sediba has long ape-like arms. The moment we had that discovered, we knew exactly what the hand would be, because that is the arm of a climber. And we knew that the hand would be long with curved phalanges for climbing, because that's what other Australopithecines look like. That's what apes look like, except the hand was sitting at the end of that arm, and it didn't look anything like that. That's the most human-like hand that has ever been discovered out of Homo sapiens and Neanderthals. We don't have any Homo erectus hands, so we don't know what they look like, but it is not an Australopithecine hand. In fact, that hand at 2 million years is more advanced than the hand of Homo habilis, which was the first early member of new species put into that genus, but is almost 300 to 400,000 years younger than this. That's an extraordinary thing. How can you have a derived advanced hand sitting on this end of this ape-like arm? The answer is we don't know. But if you ever wonder, people go, well, how can you tell from just a bit or piece that it really is a biped or it's a human-like ancestor? Here's a good example. This is Sediba's upper limb. You're going to see this part published very shortly, but you can see how long it is. This is a chimpanzee, but you can see how the scapula is shaped broad and wide at the base in order to accommodate bipedalism. And what is most striking is the difference between the hand morphology here, with this short, long thumb hand of a human and the long, curved hand of an ape. The pelvis and other parts of the anatomy are equally bizarre. This is Lucy's pelvis in the middle. That's what it should have looked like, because the cranial capacity of Sediba is only 420 cubic centimeters. That's the size of a grapefruit. If you imagine, it's amongst the smallest of any Australopithecine. And we had thought that the reason Australopithecines had these wide, stable pelvises was because they could. Humans have a tall, broad pelvis. In order to have a sort of destabilized bipedalism, it actually seems disadvantageous. We developed an entire thing. Read a textbook. It's called the obstetric hypothesis. The idea that the reason the human pelvis is inefficient like that is because we needed to give birth to big-brained babies. Sediba single-handedly proves that's not true. Every textbook's got to be rewritten because it has a human-like pelvis, but this incredibly tiny brain. We can even tell things like the female had had a child. She has indications of having the stress marks, having the child in that, and other amazing things like they have sex differences in the pelvis. We know a lot about the site. We know the site existed about 30 to 50 meters underground 2 million years ago. It was some sort of submerged sediment trap in a pool of water supersaturated with calcium carbonate, and that these hominids were falling in there. They actually have evidence that they've broken their arms. He's broken both of his arms at the surgical neck of the humerus. She seems to have dislocated her right arm as she fell, possibly sticking it out. And they are there with many other animals. They're there with antelopes. They're there with saber-toothed cats. They're there with hyenas, down to little mice, insects, birds. None of them have been scavenged. So whatever the situation that they found themselves in was so protective that it prevented scavengers from getting to them. They were buried very quickly and cemented like Jimmy Hoffa being poured into concrete. And that's why we have this extraordinary, remarkable situation. Almost every animal we find is the most complete that has ever been discovered in the history of Pleistocene paleontology on the continent of Africa. We're able to do, because of their completeness, fairly remarkable reconstructions. This is Carabo in the middle. This is Lucy here. And this is Turkana a Homo erectus that's about 400,000 years younger. You can see the lengthening of the legs, but still the maintenance of an abnormally long arm, but not an increase in the head. This is a remarkably complex transition that we as a field of science did not expect, and we don't know what to do with it. As I said, it sits at a critical time period, right at the transition between this group of Australopithecines and whatever comes next. We don't know whether this is that transition or not because it's so unexpected. We probably will find out eventually because the skeletons I'm showing you are not alone. They are there with many other individuals. We have found at least 4 other skeletons in accompanying at least 2 infants, an adult, and at least another juvenile, at least, and we haven't excavated yet. We are going to see from this site potentially the most extraordinary look at a population of early humans that anyone has ever seen. We've also been able to apply really cool technology to it. You may have noticed that the rock was still left underneath the skull. That's my team's gift to future scientists, 100 years, 1,000 years, 10,000 years from now. That's the record of where we found them as technology improved. And the reason I can afford to leave that time capsule for future generations of scientists is that I can make the rock disappear now. I can then take a skull out. I can take the various pieces that we find in the rock. I can put them back together. And then I can, of course, make it invisible. And yes, what you're seeing there is, in fact, a fossil brain. You may wonder, how can you have a 2-million-year-old fossil brain? Well, the answer to that is that every time your heart beats, it pounds out effectively an image of the exterior of your brain on the inside of your skull. By taking the scanning technology, we can pass through, reverse that image, and of course create a replica of Sediba's skull. And it, of course, doesn't look like what it should, just like the rest of its anatomy. It has a 420 cubic centimeter brain, but as you can see from this, it's bilaterally asymmetric. That's an advanced trait, very similar to ours. And also, if you're very careful in looking, you will see that as this turns around, it has a bulge in this area, which is called Broca's area, which is often associated with language. So there appear to be some changes, reorganization going on before encephalization, before brain size increase. That's got to be rewritten too, because that was completely unexpected from our previous record. You can see also we can do cool things like look at the developmental age, look at various parts of the interior structure that we just didn't have the capacity until very recently to do. This is the most expensive picture you will ever see produced in your life. I don't care what you have on your walls at home. This machine cost 6.5 billion euros to produce this. It's a synchrotron, 2 weeks in front of that, to create this image, which is a 0.075 micron reproduction of that skull. The most accurate reproduction passing through it ever done for an early hominid. It's allowing us to look right down to the basic building structure of these. We can actually look down to the point of looking at the daily incremental growth lines and teeth. So you will know eventually how old that little child was to within 9 days of his death 2 million years ago. That's pretty cool. So what did I learn from all this and what I'm going to leave you with? Well, a couple of things that I would like to leave you with here. One is that I think that a lot of people out there in the real world, and particularly children, feel that all the cool stuff has been discovered. That basically what we will do out there in the natural world is follow in the footsteps of great explorers. That we've explored this planet over the last 300 or 400 years. We've set foot on it. We've climbed all the mountains. If you're going to get in National Geographic, you have to climb naked up the south side of Everest with a dead parrot on your shoulder if anyone's going to pay attention. That if you're going to make big contributions in business or engineering or science, it is going to be incremental in its growth. Maybe even in software engineering or the internet and such as that, because it's all been laid out. What this discovery says is that is not true. Sitting there in the middle of the most explored area on planet Earth for these very objects, so easy that a 9-year-old could see it, was not only just another piece of one of these, but maybe the best that have ever been discovered to date. That means, absolutely, that we have not explored this planet. We may have walked all over every square inch of its surface, but we have not seen it. What is now going to happen is that this generation is going to be privileged enough to utilize technology, crowdsourcing, to actually see and understand what we've been stepping on this entire time. The second thing that comes out of this is that we humans have a tremendous sense of backyard syndrome. You all know what backyard syndrome is? Backyard syndrome is this. If I do an exercise with you, I say, look around this room that we're sitting in right now, pay special attention to it. And then we walk outside to that coffee shop, and I said, okay, I want you to draw this room, and I want you to draw your backyard, or your living room, or your kitchen, something you're intimately familiar with. You will do a better job of drawing this room than you will your backyard, because your backyard is actually in your brain an amalgamation of all your experiences with it. It looks like what your backyard looked like 2 years ago to the present. It's why you will find a Post-it note on your refrigerator from 2 years ago reminding you to do something you didn't do. Because that's how our brain works. We're protected from the normal until there are gross differences that are seen. There was a fossil and a site sitting in the middle of the most explored area on planet Earth by scientists, by people looking for these very things, and we missed it. My colleagues and I had backyard syndrome. It took the eyes of a child who had no expectation of non-discovery to actually find that first piece. This has been an extraordinary situation for us. It's been a humbling experience for my team. I went from an organization that was going to be closed to an organization with more than 100 scientists from around the world. We represent one of the largest focused scientific project on the planet. All in this short space of time, all based upon the discovery by a 9-year-old of a clavicle. And that's why, if some people would ask why we've written things like this children's book first, because it did touch children. This idea that first they could contribute, they could participate in big science, and it isn't just a fluke of discovery. It's not just that Matthew said, Dad, I found a fossil with no knowledge. He saw something different. Remember that the rest of us had to spend hours and hours to actually gain that childhood phenomenon. So ladies and gentlemen, it has been a privilege to talk to you here at Google. You, as I said at the beginning of this, have done more for the natural sciences and sciences with your open access and freedom than almost any other. I can tell you, you have been an inspiration for my large team of scientists. We are probably the first team in a very competitive, contentious field that have completely opened access to these fossils. Any scientist can look at these fossils at any time, published or unpublished. And a lot of that is due to the inspiration that organizations like yours have done, in the very sense that it was the free access to information that in fact was very much responsible in the beginning for making this discovery. Thank you very much. So yeah, how I would balance that sort of thing is I don't. I literally have not spent more than a minute and a half at those other sites, and I didn't have a 9-year-old with me when I went back to them. But what I'm doing now is trying to train the next generation of explorers. We need to get people out of the labs. We have done a tremendous job of training for the last 30 to 40 years laboratory scientists. We're great at analyzing the small amounts of material I have. What we have not trained is a great deal of people with an awareness that there is more out there to be discovered. In fact, in 2000, a major scientist in the field, actually from this particular region of the world, said there were no new fossil sites to be discovered on the continent of Africa. We had pretty much found the entire trend. Something like this proves that wrong. That also, though, engendered a spirit of a lack of exploration and discovery in our field that we need to kill. It needs to be killed. Things like this will kill it. But we're actually going to begin training deliberately young explorers. We're building exploration academies that train not only people in paleontology, but all the fields. Because if it's true in my field, it's true in your field. I don't think it's, I just think it's right next to a city. The fact is that a lot of the discoveries happen there. Like many discoveries, what that does is become this magnet for people to go back, because we love safety, don't we? If he found it here, I'm going to start in the cave right next to it. Then I'm going to start in the one just out of that. These dolomitic limestones cover huge regions of Africa. You can find them in Zimbabwe, Mozambique, Zambia, Angola, Uganda, the Congo. Huge regions of Africa, unexplored. You can find them in Eastern Europe. You can find them in India. You can find them in China. I'm working with the Chinese now and looking at building exploration instead of just working in sites that were found by Westerners in the 1920s and 1930s. We need to just get out there. It's not going to be a miracle. It's just going to be that we haven't been looking. I know it looks like bone. It's not bone. It has been replaced. What you're seeing here in this particular sense, although the preservation is very good, the kind of yellowish color is actually due to calcium phosphate, a large amount of phosphatic materials from bat guano and things replacing into it. It's been replaced heavily by calcium carbonate, manganese, magnesium, and other minerals. That's not bone. The teeth are absolutely the same teeth that were in their mouth, interestingly, because it's already a fossil in your mouth. It's a hard substance. However, having said that, there is organic trace in this. And that because of the extraordinarily interesting way in which it was preserved, very suddenly, very quickly, it is preserved very surprising levels of organic material, and that opens up potentials of exploration that are really quite exciting. We think it was probably almost like a sinkhole environment, but almost like a pitcher plant, and it probably had water in it. Well, they were preserved in water, so we know it had water in the bottom of it. And we probably think that all of these animals were going after water. Water is about the only thing in the world that an animal will take a life or death risk for. We tend to forget, because we're nice and civilized, how important water is. But if I put you on a 30-meter platform that you couldn't reach the pole underneath, and I put you up there with all the water you could drink, I could come back in 2 weeks and there'd be a skinny you sitting alive up on top of that platform. If I put you up on that platform with non-liquid foods, and I put a glass of water at the bottom, 48 hours, you might make it 72 before I'd find your body at the bottom of it. And these all seem to have indications of breaks and falls. They were desperately trying to get down there, and they wouldn't do it for food. You're mixing animals, carnivores, herbivores, omnivores together into this strange mix of things, and the only thing that unifies them is water. That's precisely what was happening when I found those 600 or so other sites. I learned where the direction of flow would be along fault lines and such as that. So I didn't always have to see a clean cluster of trees like I described to you. I was finding them also without that. It's also the kind of thing that we're now applying, and we can put into computers and programs to actually do that in areas that we haven't explored yet. Once we ground truth a little bit, we can find these patterns and actually use them to find more. That's going to offer an explosive rate of discovery, I think, in the next decades. In this particular case, there isn't a cave, although there may be a cave underneath. We're about to do ground-penetrating radar. As you move up the hill, there are lots of real caves in the ones that you would think of, and some hold fossils, some don't. It's really like, imagine a block of Swiss cheese, and imagine the holes you can't see are real caves, and the ones where the cheese is cut are these. And they've been infilled by various materials, so some of them are little holes, some of them are big holes, and it depends on where the luck of where you are at that particular slice on the form and shape of that hole, although all of them were at one time a cavity within the earth. We're going in that direction. We're using things. We're working with like the Safari program, which with the U2 flyovers that look at things like spectral imaging and all of that. We're looking at magnetics. we're looking at all kinds of ways to establish the existence of these. What it will require, though, is another generation of strong field work, where you're getting out and ground truthing the existence of these and then relaying it back to these enormous and fantastic data sets that we're accumulating. That's why things like, Google Earth, as it improves, and the quality of that are so important, because it's going to launch this resource base for the future of fossils. You may very well see a situation very, very shortly that these are fast becoming not the rare sought-after objects. They'll still be sought after, but they may not be rare. If you'd asked me that 3 or 4 years ago, I would have waffled on around, well, they lived in broken woodlands and we take the animals. And the beauty of this site is it collected over a period of sort of probably a few weeks to at most a couple of months, the entirety of the assemblage. We're finding organic remains, plant remains, seeds. We have things like fetuses of antelopes inside of their mothers inside this. We're going to give you the time of year within a couple of weeks that this happened. We're also going to give you a texture of environment that's unprecedented. You're going to see a real environment reconstructed. I'm not going to tell you what that is right now because we're building this super accurate picture, and anything I tell you would in fact just be a disservice to the quality of the information. We will know. I can reveal this, that we just recently, because we were scanning with these high-resolution scanners, scanning the blocks, we found out that the blocks themselves are not rock in the way we thought. They're actually comprised of organic material like leaves and seeds. We've been destroying the very evidence we'd always been looking for of the actual environment, and they're buried in it. And we were taking it away in order to figure out what the environment was that they lived in.
Kind of like peat.
Yeah, but of course it would be. Imagine the bottom of a cave with trees and a world out. Every time it rains, that material gets washed in, leaves fall in, an animal drops in. It's an organic compost, if you will. It's exactly what's in the bottom. You mix a high degree of calcium carbonate coming out of the dolomitic limestones, the water supersaturated in calcium carbonate, add some fine silts into that. It is a perfect environment for fossilization. We're hoping so. We're hoping that we will be the generation of scientists that minimizes the destruction of material. If I'd had even a portion of the rocks that were attached to some of the great fossils like the Tong Child or Lucy or these things, we could do so much now with them. We could date them. We can't date them anymore because that material's been removed. We could tell the environments and that sort of thing. We have recognized that, and we're the first team that's backing off of that material and saying, no, first we've got to push technology. So this large block that my wife Jackie discovered has got this skeleton in it, and I'm not letting it be prepared, even though there are bones in there that we have never seen in the history of searching for human origins, complete femurs and stuff. I'm making them push the technology before I will touch that to try and extract them, to try and make programs that will actually see into this and extract them in a quality that we can use, because it might be the last time this happens. And if we don't invent that technology, who's going to invent it? And you need something big enough to drive the kind of R&D that it takes to push the field in a direction, and this is big enough. Excellent question. Next. We, as you might imagine, are expending every effort working with the very finest labs in the world who work on that, because it's impossible. There will be no 2-million-year-old DNA. Of course there won't. However, we have certain things preserved that may give signals that things like amino acids were preserved. And if amino acids were preserved, you might have proteins. And so, good question. That's probably a good one to end on. Thank you very much, everyone, for your attention.